Chapter 12, we look at graphing trig functions quite a bit, and today we're going to look at sines and cosines. So the graph for sine and cosine generally looks the same. The A tells us the amplitude. B allows us to find the period. We take 2 pi and divide it by b. We use 2 pi because that's the typical length for a regular sine or a regular cosine graph, because that's once around the unit circle. C and D behave just like those numbers have in any other function. C gives us a horizontal shift, D gives us a vertical shift. C is sometimes referred to as the phase shift. The graph of sine x has a regular period of 2 pi and an amplitude of 1, and it looks like that. The regular graph for a cosine, the graph of cosine x, has a period of 2 pi, amplitude of 1, and it looks like that. And of course, this is one period of the graph, one cycle. These things go on forever, both directions, repeating themselves. So I want to graph 3 cosine 2x minus 1 on the interval from 0 to 2 pi. So I'm going to start with making an axis, xy, and the 3 is the amplitude. So I'm going to mark off 3 up and 3 down. The period changes here because there's a coefficient of x. There's a coefficient on that. B is 2. So we're going to take 2 pi divided by 2, which is pi. So there's pi, and I'm going to mark the middle of this interval. So I'm going to mark out this period into 4 intervals, because that tends to work nicely for these curves. There's kind of 4 parts. And then I do need to go all the way out to 2 pi. So I'm going to be graphing 2 cycles of this graph. The way I like to do this is to ignore the shifting first. Now the deal here is that this minus 1, that is D. That's the vertical shift. If it was a horizontal shift, it would be in parentheses with the x. So this graph is going to go down 1 unit when I'm done. But I'm first going to plot points that would be on the unshifted graph. So this graph starts at 3. At the end of the cycle, it will be back at 3. Halfway through the cycle, it will be at -3. And then at those spots. And I'm going to label off some more of these values here. And then the cycle repeats itself. For my finished graph, I'm just going to take all these points and drop them down 1 unit. If there was a horizontal shift, I'd also be sliding them to the left or the right also. If you can do this all in one shot without making these original starting points, fine, doesn't matter. I find it helpful to do it this way though. So here's our finished wave.
Please, Aaron Burnett to the student office.
To model this data using a sine function, first we need to plot it. So here's the data graphed over a 2-year period. Since it's the mean temperatures, this trend will repeat itself the next year. And we can see clearly that this is definitely some sort of a wave. What we need to look at is period, amplitude, shift, so that we can write our equation. Usually, wave equations are written using sine out in the real world. So to find the amplitude, what we can do is take the maximum minus the minimum, that would be the difference of them, and cut it in half. Therefore, A will be equal to 6.5. For the period, the period here is 12. And we know that has to equal 2 pi divided by b. Therefore, b is pi over 6. For the vertical shift, or what the book calls the principal axis, we can take the maximum plus the minimum and divide by 2. We can find the mean. That's going to kind of be the middle of all this data. And that's going to give us D. So this yellow line that I'm putting in approximately models that principal axis. We need to find C, the horizontal shift. And what we want to look at is we want to look at where this curve might be starting. And here is one normal sine cycle. And there's actually a point right here that is 21.5. And the shift that took place is 10 months. So C is equal to 10. So our equation is going to be T equals 6.5 sine pi over 6 times T minus 10 plus 21.5. Where capital T is the temperature and little t is the number of months. We could also use technology to model this data, and I'm going to walk you through doing that right now. In your graphing calculator, we're going to go to the Stat menu and Edit, putting the month in list 1, and I'm just going to use 1, 2, 3, 4, 5 for January, February, March, April, May, so on and so on, and I put the temperatures into list 2. If I want to look at this data on my graph, I need to go to my stat plot and turn this on. The type is set to scatter plot, and I want my X list to be where I put my X numbers and my Y list to be where I put my Y numbers. And then I'm going to zoom stat. That will automatically fit my window to my data. And so here's my curve. Now I want to come up with the equation of best fit. I'm going to go back to my stat menu. I'm going to go to calc. I'm going to go down to sine regression. And I'm going to specify that I want list 1 as x and list 2 as y. And then I'm also going to store this as an equation in the calculator. So I'm going to put a third thing after this. I'm going to press my variables key right next to clear. I'm going to go to y variables, function, and I'm going to select y1. This is automatically going to store the values for a, b, c, and d into my y equals. Now you might notice that c is different here. C is not the same as what we got. We got c to be 10. Here we're getting c is 0.96. The other thing to notice is that it's plus up here in the equation. If we look at what this equation really is, we're just going to look at part of it. Sine 0.52 x plus 0.967. Our equation had the b value pulled out in front of the parentheses. So if I do that, I get 1.86 in here, and that's about 2, roughly. So this is saying that the horizontal shift, the way that we're used to seeing it, c is negative 1.86. We're about negative 2. If we go back to our graph, a shift of 2 to the left puts me over here, which should make sense that that would be the start of another sine wave. If we look at this graph now, if I hit graph, there's our points, there's our curve going through them.